Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. So in these sections, we will look at the Reynolds transport equations. So if we recall basic laws, for example, the mass conservation equations, the momentum conservation equations, or the Newton's second law, and the energy conservation equations, or the first law of thermodynamics, are applicable and formulated in terms of systems, meaning that we are using the Lagrangian viewpoint. Whereas when we analyze fluids, normally we will use control volume analysis. Thus, for control volume analysis, i.e. using the Eulerian viewpoint, the governing equations need to be reformulated. So if you recall the definitions of control volume and systems, control volume is any volume of constant shape, size, positions, and orientation with respect to an observer. Control volume can be of finite size, or it can also be of infinitesimal size. For a control volume, matters as well as heat and work can cross the control volume surfaces. Whereas in a system is a fixed mass with a boundary. It can also be of finite size or of infinitesimal size. For systems, heat and work can also cross the system surfaces, but mass or matters cannot cross the system's surfaces. So let us consider a control volume with multiple inflows and multiple outflows. So this is the control volumes and systems. So this control volumes has two inlets, inlet number 1 here and inlet number 2 here, and then two outlet number 1 here and then outlet number 2. So let us consider what happened to the control volume boundary and the system boundary at time t equal to t initially, and then at time t equal to t plus delta t after fluid has entered and leave the control volumes. So at time t equal to t, the control volume surface is as shown by the solid line here. At time t plus delta t, the control volume surface is still the same because in a control volume, we are dealing with a fixed shape. So the solid surface here represents the surface of the control volume at time t and at time t plus delta t. If we consider the system, at time t, the surface of the system is exactly the same as the surface of the control volume, as given by this line here, which is made up of a long dash and a short dash. Whereas at time t plus delta t for systems, since we deal with this fixed amount of mass, we have to minus the mass which has entered the control volume at inlet number 1. So similarly for inlet number 2, the shape of the system would change such that we have to minus the mass which has entered the control volume. Whereas at outlet number 1 and outlet number 2, some of the mass which were originally in the control volume now has exceeded the control volume. So for the system, we have to consider that original mass which has now exceeded the control volume at outlet number 1 here, as well as at outlet number 2. So this table here gives a summary of the shapes of the surface of the control volume and surface of the system at time t and time t plus delta t. So we can see that at time t plus delta t, the shape of the control volume surface is the same as at time t is equal to t, whereas for the system, the shape are distorted such that we have to minus amount of mass that has entered the control volume at inlet number 1 and inlet number 2, and we have to add the mass which has left the control volume at outlet number 1 and outlet number 2. So if you consider at time t equal to t, so initially when t is equal to t, so we can write xct is equal to xst. Okay, xct is equal to xst. Whereas finally, when t is equal to t plus delta t, we can write xc t plus delta t, this here, is equal to xs t plus delta t. This is xs t plus delta t, this one here. Then we have to add amount of mass which has entered the control volume, so plus dx which has entered the control volume for all the inlet. Then we have to minus x which has exited the control volume for all the outlet. Right. So now we can write the rate of change of x inter control volume. If we take these equations minus this equation here, so we can write x c t plus delta t minus x c t divided by delta t, and this must be equal to this minus this, xs t plus delta t minus xs t over delta t. So I can write this as the xc by delta t, and this is delta xs by delta t, and then we have another this term here which is actually equal to delta x by delta t for all the inlet, then minus delta x over delta t for all the outlet. Right. So now I can continue in a limit as delta t goes to 0. So I can write the equation which says that dxc by dt is equal to dxs by dt plus x inlet for all the inlet minus rate at which x goes out of the control volume for all the outlet. So we have these equations. This is actually the general control volume equations, or this is actually what we call the Reynolds transport equations, RTE, right? And then if the flow at inlets and at exits is non-uniform, then we need to write the general equations for non-uniform flow. For general non-uniform flows, okay, so this rate of change here, we have to do integration, so d by dt rho x d volume must be equal to dxs by dt, this term here, but then the flow rate at inlets and exits, as per what we derived in the last part of the chapter for all the inlets, this will be equal to rho ux dA inlet minus for all the outlet rho ux dA outlet. So this is the general Reynolds transport equation for general non-uniform flow. So I need to put a note here. Note that X is actually the equivalent intensive property, or this is the property which is per unit mass for X. So this is the equivalent extensive property, right? So I can write a summary of the equations. So the Reynolds transport equations that we have just derived just now, so which is dxc by dt is equal to dxs by dt plus all the inlets x dot inlet minus all the outlet x dot outlet. And for non-uniform flow, d by dt rho x dv is equal to dxs by dt plus for all the inlets rho ux dA inlet minus rho ux dA outlet for all the outlet. So we have seen just now that the Reynolds transport equations, or the general control volumes equation for multiple inflows and multiple outflows, is the rate of change of x for the control volume is equal to the rate of change of x for the systems plus the rate at which x enter the system minus the rate at which x exit the systems. Or for non-uniform flow, the only difference is that we need to integrate in order to obtain the rate of change of x in the control volumes and the flow rate at inlets and at exit, because the velocities are non-uniform. So by using this Reynolds transport equation, we can now apply the conservation law to a control volume. If the flow is steady, then the rate of change of x for the control volume will be equal to 0. So for steady flow, we must have the rate of change of x for the control volume must be equal to 0. So that means that this term here are 0. So this implies that we will get the Reynolds transport equations will be equal to dxs by dt is equal to x dot out for all the outlet minus x dot in for all the inlet. And for general non-uniform flow, since this term here is equal to 0, then we're left with this term. So we can write dxs by dt is equal to summations for all the outlets rho ux dA outlet minus for all the inlet rho ux dA inlet. So these are the Reynolds transport equation for steady flow. So for steady flow, as per what we have just derived, we will get these two equations here. So the rate of change of x for the systems is equal to rate at which x exceeds the control volume minus the rate at which x enter the control volumes. So similarly, for non-uniform flow, we have to integrate over the inlets and exits in order to obtain the rate of flow of x at inlets and at exits. And note that the first terms here, the rate of change of x of the systems, is related to system-based physical law. For example, if x is equal to momentum, then the rate of change of momentum for the systems is equal to external force by using the Newton's second law.